Uh, Hello everyone, good afternoon. And today's experiment is on finding the DFT of square, sine and rectangular pulses. So in today's lecture, the flow of the slides is something like this. So initially we will see some of the basics regarding DFT and FFT, and then we will see some of the signals such as Sinc signal, and then we will see some of the MATLAB functions that we will be using in the program, and finally we will see the demo of the program that we will be using here. So initially regarding DFT, I know that you have used a DFT, you have computed DFT earlier in other experiments. So here mainly DFT is used to calculate the spectrum of a signal, especially if it is a finite duration signal. Is not so applicable. In such a case, the signal frequency content becomes more useful in certain scenarios. So especially DFT is used to represent or to note the frequency component of the signal. And regarding the FFT is one method of computing the DFT, and as mentioned here, so the first line says that the algorithm that transforms the time domain signals to the frequency domain component is known as the discrete Fourier transform, or DFT. And what is FFT? FFT is the way of implementation of DFT. Since FFT, DFT can be computed, you have seen using some equation you can find the DFT. But FFT, using FFT method, the computation of DFT is more efficient and much faster. So you can see here in the next slide that DFT can be computed with a time complexity of O of n square when you have n, you want to find n point DFT. Whereas if you use FFT to compute the same, the time complexity will be O of n log n. So that is much faster. Using FFT, the computation of DFT is much faster. Okay, so now we will move on to the first signal, or we want to find the DFT form. The one is the square wave. You know how is the structure of a square pulse, and then we also have to find the DFT of the rectangular pulse, rectangular function, and the third one is the Sinc function. So I'll be talking about Sinc function more in detail, whereas the square pulse, the structure of a square pulse as well as the rectangular pulse. So I'll be seeing only the program, how to compute the DFT of those functions, but whereas regarding the Sinc function, I'll give some more details here. So Sinc function is an important function when you consider any signal processing or communication engineering perspective. So it's an oscillatory signal as mentioned here, and also the Sinc function is sketched here. So I open the pointer here to show you more in detail. So the Sinc function is represented here. So this Sinc function, if you observe here, it is symmetric on the left hand side as well as on the right hand side. So it is symmetric with respect to this axis. So this is an even function, but this function has a maximum value at the 0 point here. So this is the x-axis or the time axis. So this is the value here. Along the y-axis you have the value of this function. So it has a maximum value. The value is 1 at this point. It's at the origin, and later on as we continue this wave, it attains zeros at these points. For example, pi, 2 pi, 3 pi, and so on. Similarly, on this side, on your left hand side, when we see minus pi, minus 2 pi, and so on, it has a 0 value here. So with this observation, we can represent sinc function in this way. So sinc function's value at 0 is equal to 1. So as we see here, at 0th point, its value is the maximum 1. And later on, it keeps diminishing. It becomes lesser and lesser as we progress, as the wave progresses. So the progressing direction is given here, plus infinity to minus infinity. So altogether, in general, the sinc function can be represented in this way. Sinc function has a value of 1 when the x value is equal to 0. For instant x is equal to 0, its value is 1. That's what shown here. At 0, it has a value of 1. And in other cases, if you see other points along the horizontal axis here, its value can be found using this equation, that is sin x divided by x. So even for 0, you can find that by L'Hospital's rule, it gives you a value of 1. And for any other instances, for example, other than zeros, maybe here or here, what's the value of the sinc function? That is defined by this one. You just need to substitute the corresponding value of x here as well as here. That gives you the value of the sinc function. So as mentioned here, the general characteristic is it monotonically decreases as we move along the positive or negative infinite directions. As you move along this side or this side, the value keeps reducing. So this is a very special function or a signal, for especially in case of communication, because of this property that it has a high at one point, that's at a 0th point, and in other places the value keeps reducing. Mainly useful to avoid the interference. For example, if you consider and you multiply with some other signal, it still maintains this property. The combined signal still maintains this property of 0 crossings at these intervals. For example, at 2, 3, 4, or minus 2, minus 3, minus 4, and so on, it still will have that 0 crossing that enables the prevention of intersymbol interference. Okay, so we will be finding the DFT of this function also. Okay, now we will see some of the MATLAB commands that we will be using in today's program. The first is the meaning of this, or what's the function of this. So it basically returns an array of zeros where the size vector sz defines the size of x. So here this one is a vector that gives the size of x. We will see an example to understand this more in detail. For instance, if I mention zeros of 2 cross 3 matrix, then it returns a 2 cross 3 matrix with all zeros. So we will see another example here. For example, you may type in the command window of the MATLAB x is equal to zeros of 1, 3. So what's the meaning here? So this is a matrix 1, 3 of the order. So 1 row and 3 columns. So you will get the resultant outcome of this function as all the zeros of this order. So 1 row and 3 column consisting of all zeros. Next, another function that we use here is y. Y is equal to ones of m, n. So y is equal to ones of m, n. That's in general. So it returns basically again a matrix of m rows and n columns, all containing ones. For instance, here you may use this command in the command window of the MATLAB to understand how it operates. For example, A is equal to ones of 2, 4. That means it's a matrix of 2 rows and 4 columns, and elements will be ones as shown here. So here we have 1, 1, 1, 1. In the next row also we have 1, 1, 1 and 1. Okay, now as shown here. Okay, now we will move on to see the other command that we will be using today. So y is equal to FFT shift of x. So the command that we use is FFT shift. So we have already used the command, I guess you have used it, FFT. FFT basically computes the FFT of the variable you mentioned here. So FFT shift will operate on this input x and produces an output y. So what actually it does? It basically rearranges a Fourier transform x by shifting the zero frequency component to the center of the array. So basically it shifts the zero frequency components to the center of the array so that we can observe the FFT, that is what we generate, in its entirety. So if x is a vector, then FFT shift swaps the left and right halves of x. We will see this, what's the meaning of this sentence, or in general what's the function of FFT shift with the help of an example. The other case is if x is a multi-dimensional array, then FFT shift swaps the left half spaces of x along each dimension. So we will see that here. For the first case, I'm using the same command here, FFT shift. So A is equal to FFT shift of a matrix here. So it's a vector here, 1, 2, 3, 4. So when I run this command, I will come to know what's the operation of this FFT shift command. So A will have this value 3, 4, 1, 2. What's the meaning here? So basically it has shifted this part here. 3, 4 has come here and 1, 2 has gone here. Okay. And then for the second case, if x is a multi-dimensional array, then what's the functioning of FFT shift? How it operates on this input when the input is a multi-dimensional array. That is shown here. For example, A is equal to FFT shift of this matrix. For example, we have 1, 2, 3 in one row. The second row is 4, 5, 6. So it's a 2 cross 3 matrix, right? So when we run this command FFT shift on this matrix, which is 2 rows and 3 columns in size, how FFT shift will alter this input. So that is shown here. So you may notice here the 6, 4, 5, the second row, and also along the horizontal direction, row wise, there is a shift. For example, 6 is here, 4, 5 are here. So if you consider this, 6 has come to the as the first element, 4 and 5 are the second and third elements. And in the input, what we have is 1, 2, 3, which is the first row. Now in the output, after the FF, second row. And the last element here becomes the first element of this row. And the first 2 elements becomes the last 2 elements in the second row here. So basically, for a multi-dimensional vector, what it does is basically operates on the vertical direction. So to say the second row has become the first row as shown here, and first row becomes second row, and horizontally these column items will also shift. For example, instead of it is 4, 5, 6, it has become 6 and 4, 5. So horizontally it does the shifting, as well as vertically it does the shifting. Second row becomes first row becomes second row, and so on. So that's the operation of FFT shift. So we can see also another example as given here in the first line. So FFT shift will be shifting the zero frequency components to the center of the array. So if you see here, A is equal to FFT shift of this vector. So 0 0 1 1 1 and 0 0 you have. So when we run this here, when we run this, the output becomes something like this. These 4 components will come here, and these 3 components will move here, right? So it becomes 1 1 0 0 0 0 and 1. So all at the center you can see all the 0 components, and ones have all moved to the left as well as right. Right? So we have all the 0 components at the center here, and 1 components are at the sides, left as well as right sides. So this is the operation of FFT shift. With this, we have one more command that we will be using, that is absolute value of some variable here z. For example, y is equal to absolute value of x, then what will be the outcome? It returns the absolute value of each element in the array x. So if x is complex, then absolute value of x returns the complex magnitude. So basically it gives you the absolute value of whatever input you mention here as x. For instance, x may be a matrix here. So the values are given here. Maybe this is a column matrix. We have a transpose here. So y is equal to absolute value of x. When you compute this absolute value on this matrix x, we get these outcomes. For example, 1.3, there is no change in its magnitude, 1.3. The second one, it has a negative sign here. When you compute the absolute value, it just gives you the magnitude. Similarly, the third value is the same, and the fourth value, we have a negative sign in the input, but basically absolute will compute will give you the magnitude. So it will give the value 5. Similarly, when there is a negative sign, it just gives you the absolute value of the magnitude. Similarly, if you consider a complex signal a plus ij, then it computes the magnitude. You know how to compute the magnitude of a complex signal, right? So that gives you the absolute value, a square minus b square, because we have a plus ij format. Okay, then now we will move on to the program that we will be using to find the DFT. First, let us consider a square pulse. So our input is a square pulse. We need to compute the DFT of the square pulse. So we use these commands here to compute the DFT of the square pulse. So you know all these commands, clear, close, all these commands. And then the actual program starts from here. X will hold something here. So x is equal to zeros of 1, 30, ones of 1, 30, and zeros of 1, 30. Because we need to generate a square pulse to compute the DFT of that. So x will represent the square pulse. So in order to define the square pulse, we will be using this zeros and ones function. So when we give zeros of 1, 30, what do we get? This function we have seen earlier, zeros of a, b gives you what? It gives you, in this case, zeros of 1, 30 gives you a row consisting of 30 columns where all the elements are zeros. Similarly, ones of 1, 30 gives you what? It gives you a row, single row consisting of 30 columns where all the column elements are ones. Similarly, zeros of 1, 30. So basically, it's like a square pulse. You have first all low and then high, again low. So that is a square pulse, right? And the duration of each pulse is the same, 30, 30 and 30. That means equal duration. The duty cycle is 30 low and 30 durations high, and again 30 durations low. And then, so at this point, at this line, we will be generating a square wave or square pulse. Basically, we're just generating a square pulse, single pulse, and that is held by the variable x. And now here in this line, x is equal to FFT of x. So basically, this x will compute the FFT of the square pulse. So we have seen earlier, in your earlier experiments, you have seen what is FFT. Okay, that FFT is computed and stored in x. And then in this line, x1 is equal to FFT pulse. So that is operated with the FFT shift. So we have seen this FFT shift. Suppose it is a vector. What's the operation of FFT shift? Or it's a multi-dimensional array, then what's the operation? That we have seen in the previous slide when I described the function of FFT shift. So the same operation takes place here on the FFT of the square pulse, and that is held by the variable x1. Okay, now we want to plot all these components. For example, we want to plot the square pulse as well as we want to plot its FFT. Now we have the first subplot 2, 1, 1. So in this subplot we will be plotting x. The x here, x is a square pulse that we will be plotting here, and we title that particular subplot as a time domain representation of the square pulse. And then we also need to find out the FFT. We want to plot it. Already we have the FFT here, but we need to plot it. So subplot, we are having another subplot 2, 1, 2. So the second subplot where we will be plotting the absolute value of x1. x1 is the shifted version of the FFT. Now we will be plotting that, only the absolute values, because the FFT may have a plus ij, that format. So in that case it computes only the absolute values, or it may have some negative values, so it computes the absolute values only. In plotting, during plotting it considers the absolute values, and we title that as the frequency domain. So this basically gives us the FFT. This plot gives us the FFT of the square pulse. So we have used the FFT shift. That is because we want to put all the zero frequency components to the center here. So we use the FFT shift. Okay, so this is the program for DFT of the square pulse. So initially we generate the square pulse here. In this line we generate the square pulse that consists of some duration of low or zeros and some duration for high, and again some duration for low. So that actually represents a square pulse. And then in the next line we compute the FFT of that, and then we slightly shift the FFT because we want to have all this. This FFT should be in a way so that we can represent it visually. So we do that FFT shift operation, and then we try to draw or plot these square pulse as well as the FFT of that square pulse here. Okay, so the MATLAB view is here. So right now I have the program already written here. The same program is written here for a square pulse. If you see here, you will come to know this is a square pulse, and we have X FFT, and you just shift the FFT, and okay, that's the same program here. And then we go for a run. We just press the run button here, and when you run the button, program runs and gives you this output. So here you may notice that from 0 to 30 you have all zeros, and next to 30, that is 30 to 60, you have all ones, and then remaining 30 you have all zeros. This is what we have defined in the square pulse X, right, with the help of zeros and ones command. And then when we run the code, we get the shifted version of the FFT here. So you may also, so you can notice that here all these components are shifted to the another corner. So by doing FFT shift, we will be pushing all those components to the center, and also we will be flipping horizontally. So without shifting, it looks something like this. You just cut the figure from here at the center into two pieces, and one piece will be at this corner and the other piece will be at this corner. So we use the FFT shift to make it all together at this point so that we can visually represent that. Okay, then let us move on to the next function, that is next program, that is finding the DFT of the Sinc pulse. So here the general operation remains the same. First we need to generate the Sinc pulse, and then we will be computing the DFT with the help of FFT and FFT shift commands. So firstly you have this clear and clear all those commands, and then we will be defining the Sinc function here. So Sinc function is defined for this instance. For example, it varies from minus pi to plus pi with the increments of 0.05. And then for those increments, that is those horizontal axis points, we will be calling a Sinc function to generate the Sinc function. So that is held by this variable x1. x1 is equal to Sinc function of this. So these are the different instances in which we will be plotting the Sinc function along this bracket. These limits minus pi to pi will be drawing the Sinc function with the help of Sinc command. Okay, so x1 will hold the Sinc pulse, and then we have here x1 is equal to FFT of x1. That is basically here we compute the FFT of this Sinc pulse that we have generated. So that will be held by this variable x1, and then we will shift FFT shift this particular FFT signal here. So x1 is equal to FFT shift of x1. So initially we have generated in this step the FFT of the signal. I mean here the signal refers to the Sinc pulse, and in the next step we will be shifting that FFT, though there's FFT shift of x1. So that is again held by the variable x1. Any variable you may use, maybe x2 or so on. So here x1 is used. Okay, and then we want to plot all this. So we have two subplots. In the first subplot we will be plotting x1. x1 is nothing but here the Sinc pulse. That will be the time domain representation. In the second subplot we will be plotting the absolute value of x1. So x1 comes from here. So x1 is equal to FFT shift version of the FFT of the Sinc pulse. So that's what is done here. So we will be choosing the absolute values only for plotting the values. So that is what we title it as the frequency domain. So the steps are very simple here. Initially we need to have the sinc function because we want to compute the DFT of that. So we will generate the sinc function at this point with the help of sinc command, and that is computed for this interval minus pi to plus pi. Okay, and then we will draw this here, draw the or plot the sinc function here. That's a time domain representation. Also we will find the DFT or FFT of the sinc pulse here, and we will rotate or shift, FFT shift the FFT that we have computed here, and we will plot that here as a second subplot. So this is similar to the square pulse. In the case of square pulse, we had the square, first we generated the square pulse and then we computed the FFT and just shifted that and plotted it. Similarly here we have the sinc pulse and then we compute the FFT, we shift that FFT and plot both. So that is given here. So when you type this code in the MATLAB, you just have to press run. When you run the run button, you will see the output this way. So this is the sinc function that we have defined, and then this is the FFT shifted version here of this sinc function. Okay, so also even in this case you check the output without using the FFT shift. I mean, you just try to plot the output only for the FFT version of this sinc pulse. Then you will come to know how the FFT will appear like. Maybe one part of this will be at one corner, other one will be here, and when you use FFT shift, it appears this way. We will be moving everything to the center. Okay, now is the third one, that is a rectangular pulse. So here again it is similar to the first program where we computed the DFT of a square pulse, but in this case we need to have a rectangular pulse. So we first define the rectangular pulse here. X is equal to zeros of 1, 30, ones of 1, 60, and again zeros of 1, 30. So this will give us a rectangular pulse, because for some duration we have a low, then here we have a high, so for a much bigger duration, and then again we have a low here. So high here is almost double than this low, right? So that appears like a rectangular pulse. Okay, so here X, this step will generate the rectangular pulse, and then in this step we will compute the FFT of this rectangular pulse. In the next step we will do the FFT shift operation on the FFT of the rectangular pulse. Here we have computed the FFT. Now we will shift it, I mean FFT shift operation will be done here, and that will be stored in X1. Next, since we have everything ready here, we just need to plot them. So the first subplot will have the rectangular pulse that we will title as time domain. In the second subplot, we will be having the FFT version, shifted version of the rectangular pulse. You note here we again use the absolute function because we want just the absolute values or the magnitudes of the FFT. Okay, then we will title this subplot as frequency domain. Basically it represents the DFT of the rectangular pulse. So you type this these lines in the MATLAB and run the program. So when you run the program, you should be able to find this output. So we have defined the rectangular pulse here. For 30 durations it is low, and next for 60 durations it is high, and again 30 durations it is low. That is like a rectangular pulse, and then we compute the shifted version of the FFT here. So everything is shifted to the center. So this is how we compute the DFT of a square pulse or a sinc pulse and a rectangular pulse. So that is the end of today's discussion. So you just need to type the program that is given to you and then try to understand the program. I have already explained most of the steps here, and I also encourage you to check each of these commands individually. For example, you can go to the command window. For instance, here you go to the command window and consider one command, for example, absolute. So you define x is equal to 1, 2, 3, 4, minus 5 and something like that, and find y is equal to absolute value of x. Then what do you get? Try to understand from that. And also you go to help and find out what are the different cases we have with absolute, and check those cases here. Similarly, when it comes to FFT shift, maybe it's just a vector. You consider a vector and find out FFT shift, how it operates on that vector. You consider a multi-dimensional array and find out the FFT shift. You'll get the result here. I mean, if you are using this command window to execute your inputs, and try to understand every command. Similarly, zeros or ones, all this. So that gives you a better practice of learning every command. Okay, so and altogether you have all the commands here. I mean, all the entire program here, maybe a square pulse or a sinc pulse or a rectangular pulse. You just need to run the program here, run the program, and when you run the program runs and gives you the required output based on your program. For example, it's a square pulse, then you should be expecting this kind of output. Please write down your observations and submit in the appropriate link provided to you. So that's the end of today's discussion. Yes, thank you very much.